Good day, my name is Dalius Gudeika. I represent the Vytautas Magnus University Faculty of Informatics. The project was entitled Density Functional Theory Calculations in Designing Symmetric and Asymmetric TADF Emitters. And the thermally activated fluorescence or TADF mechanism is based on a second-order spin vibronic coupling between a charge transfer triplet state and a local excited triplet to mediate the upconversion reverse intersystem crossing of the coupled triplets to the emissive charge transfer singlet state. And building on the previous findings and aiming to better understand the connection between analogs DA and DAD molecules, we investigate isomeric DAD TADF emitters comprised of a benzonitrile acceptor and acridine donors attached at the 2,5 or 2,6 positions of the acceptor. And comparison to previously reported DA materials allows us to compare these systems with minimal additional complexity introduced by the second D unit. And using a combination of experimental and theoretical methods, it was demonstrated that electronic interaction between the donating moieties modulated by the relative position of each alters the free LE energy and thus also delta EST and TADF performance. And the two isomers OMACA and OOACA were synthesized by the procedures shown in scheme 1. And DFT calculation is the primary tool in predicting and investigating excited state configuration, excited state energy, and molecular geometry of TADF molecules. As with the experimental investigation of TADF molecules, most of the research focuses on excited state configurations and energies of relaxed geometry of excited states and explain experimental phenomena with discrete geometries or excited states, such as ST, free ST, and free LE states. Some researchers attempted to relate DA dihedral angel with SE and T1 images, but they have several limitations. A large discrepancy with experimental energies due to inappropriate selection of functional, lack of explanation to the effect of dihedral angel to excited state configurations or energies of S1, T1 states, or mixed level of theory for S1 and T1 leading to inverted S1, T1 energies. And quantum chemical calculations of studied derivatives were performed using DFT implemented in the Gaussian 16 software package. And to better understand the behavior of organic compounds, we turn to DFT calculations. And figure 1 shows the NTOs and energies calculated for relevant triplet and singlet states in OM, ACA, and OOACA materials. By inspecting the singlet NTOs in OMACA, we first note that the ST singlet associated with the orthodonor S1 is lower in energy than that associated with the meta-donor ST state S2. And this is in agreement with expectations and the trends established for ODA and OMDA. In OACA, the singlet 1 and the singlet 2 states are much closer in energy, and each involves both of the orthodonor units. This represents symmetric S1 and asymmetric S2 combinations of otherwise that generate ST states associated with either left or right donor individually. And this is analogs to the formation of symmetric bonding and antisymmetric antibonding molecules orbitals from combinations of degenerative atomic orbitals, and for the first two triplet states of ST nature similar trends observed. The first triplet state of LE nature is T3, centered on the A unit in both materials, and with nearly identical NTOs. And this LE triplet state is the one relevant to vibronic coupling and RISC. Interestingly, the calculated the free energies of OM, ACM, and OOACA are in the opposite order as found experimentally, with about the same difference in triplet energies in both cases. And the reason of the experimental OM-ACA triplet energy being lower than OOACA cannot be due to the combination of individual couplings of the A to the two D units. And the two materials to either have identical triplet energies of OM-ACA to have a higher triplet energy than OOACA. Any such state mixing between LE and ST states is also unlikely to be a contributing factor due to the forbidden nature of mixing these states with different orbital symmetries. And LE T3 states in both OM-ACA and OOACA interact with higher lying LE states delocalized across both donor units DD states. And a representative state diagram is presented in figure 2b, showing how these unoccupied electronic states would form. And the proposed DD states are formed by linear combinations of the individual donor and E states in figure 2b. And so one of these DD states is expected to be the lowest energy LE singlet state in each molecular system. And these DD states also unoccupied. This explains why the DFT calculations are unable to accurately predict the order of OM-ACA and OOACA T3 energies compared to experimental. And applying molecular orbital theory in the symmetric and asymmetric DAD systems, we can infer several properties of the DD states and how they would differ. Due to different conjugation strengths across the linker unit for OM-ACA than for OOACA, the DD state to be lower in energy and have larger electronic density on the central bridge region. And this would subsequently lead to a larger overlap between the DD state and the freely state associated with the A unit in OM-ACA as compared to DD in OOACA material. And the resulting state mixing between DD and free LEA states lowers the absorbed phosphorescence energies in both materials compared to calculations which cannot account for interactions with unoccupied orbitals. And due to increased orbital overlap, the state mixing with the free LEA is more expensive for DD than for MDD, and leading to yet lower triplet energy OM-ACA and the observed ordering of experimental phosphorescence energy in figure 2c. And although based on well-established principles of molecular orbital theory, much of the previous explanation is speculative. Nonetheless, some evidence for the existence of the proposed DD states can be found in the experimental absorption spectra. As you can see in this figure, in DPEPO films and a range of solvents, redshift in the main absorbance band peak at 275 nanometer in OM-ACA compared to OOACA was observed. And this redshift is due to the presence of a weak underlying band associated with existation of the DD singlet state. Furthermore, the absorbance spectra also show the same weak direct CT absorption band in both OOACA and OM-ACA at 375 nanometers. And each material, this band corresponds to closely spaced CT state absorptions consistent with the DFT calculations and prior understanding of the DA-OM-DA materials. So here we can see the main conclusions were depicted in the slide. And thank you much